So the first section for this course is 12.1 on sequences. Theoretically, at least, most of this should be a review. Sequences were incorporated a little bit into Calc 1 and Calc 2, but we'll go through everything you need to know. I won't be real formal with my definitions because I think it's pretty straightforward, the ideas, but yeah, let's just follow. So, if you recall, we'll denote sequences like this. Sometimes, well, let me just start with this. So a sequence, this is a sequence, is a function defined on a subset of Z. Remember, Z is what? Does this look familiar? Set of integers. We'll just use that notation from time to time to save us time. But really, what is a function is, I mean, a sequence. Oh, I really should find what I'm saying here. So a sequence okay, denote like that. It's just a function defined on a subset of Z. And so it's just an ordered list of things, generally numbers, right? An ordered list of numbers is what we think of as a sequence. And so let's just do some examples here. So list the first few terms of the following. And so as we go through here, I'll be using some of the terminology of sequences. And so if any of it seems unfamiliar, just ask. Okay? So it's stuff that might have been defined, may not have been defined formally, but I think it should be pretty straightforward. So here's our first one. So oftentimes we'll denote sequences just like that. Other times we'll sort of put a counter on the right-hand side that says, here's our sequence. It's k over k plus 1, and then the k's range from 1 off to infinity. Does that make sense? And so if we just want to list, so I'll just do it like this, equals the elements. And so now let's just list the elements here. So again, we just work our way through, right? When k is 1, plug 1 in, what do we get? 1 half. So there's your first element, or first term of the sequence, right? And the second term is now when k is 2, so 2/3. All right, first and next 2 of them. 3/4 and 4/5. Does that make sense?
Yeah.
How about and this time our n will start at 0. So when we said over here that sequences were subsets or defined on subsets of the integers, right? So here's our subset from 1 off to infinity. This time it's from 0 off to infinity. You could start at -10 and then go -9. But the point, they generally start at some number and then you include everything as you move up from there. Okay, so this one I want the an where the a sub n is defined to be -1 to the n and n. So we'll just list the elements down here. So what do we get when n is 0? 0. So -1 to this 0, which is what? 1, right? And then times 0. Is that okay? So you should get 0 for your first term. I'll just write this up. -1 to the 0 times 0, right? And then your second term, now n is 1. And I'll write it -1 to the 1 times 1, so that's just -1. -1 squared times 2, so positive 2.
Yes.
Is that okay? And so let's just, rather than write out any more, we'll write out some more terms, but rather than putting the top here, let's just think about what happens. Right, so what's the -1 to the n do? It just makes the sign flip, right? It'll be plus, minus, plus, minus. Whenever your n is even, it'll be plus. Whenever it's odd, it'll be minus. Does that make sense? So they'll just alternate signs, and then this just goes up by 1, right? So we got what next?
-3,
-3,
4, -5,
5, 6, and so on, right? Does that seem okay? All right. All right. So this is one direction. You're sort of given the form of the sequence inside the brackets here. Now I want to go the other direction. I'll give you a list of terms from the sequence, and then we'll try to figure out the form that it takes. I'm just moving in the opposite direction. And all of this is going to be important in this whole chapter. This chapter's on sequences and series, and so as we start introducing series, you're going to have to sort of naturally be able to figure out the sequence associated with the underlying series. So let's just do this guy 1. Oh, let me give you directions before I do anything else. Find the next term and the form of the following. I'll just say following. They're sequences. So, and actually, let me not put it in parentheses, I think. Okay. All right, so all I want you to do here is look at the sequence, try to recognize some pattern that's emerging, and then once you have a pattern, give the next term, and then once you have the next term, let's try to figure out the general form in that form. Actually, I don't know if this works better in terms of recording, but you might want to just stay on the formula, because they can hear me off to the side. I'm not that interesting.
64.
64, does everybody agree? It looks like you're just doubling it at each stage, right? And so you double it again, it'd be 64. So then I'll just write it this way. Next term, 64. And then the sequence, the form of the sequence, how would we get that?
There's 2 power of n minus 1.
2, okay, let's try that. Power of n minus 1.
Yeah.
That would be okay. Where does n start?
0. Oh, 1.
Okay, so you could do this with n starting at 1, right? Notice when you plug in 1, you'd get 2 to the 0, which is 1, right? When you get to 2, it'd be 2 to the 1, which would be that. So this would be fine. You could also have just written it as 2 to the, I'll use another, 2 to the k, right? Where k starts at 0 instead. Does that make sense? And so either one's fine. You don't need both. I probably would have written the second one, but either one's perfectly acceptable. Is that okay? All right, let's try one more here. Okay, so this one's got sort of a weird term, that 1/9 that shows up. Looks a little bit off. Don't get thrown off by it. Try to think about what it looks like happening in the bottom. What does it look like happening in the top? And maybe if 1 or 2 terms look out of place, still just try to recognize a pattern and go from there and see what you come up with. So take a few minutes, maybe 30 seconds or so, and look at this, and then we can chat about it. Okay. Any guesses for the next term?
I would say n over negative 3 power of n minus 1.
Okay. So that's the general form, right? What about the exact next term?
That next.
So 1, 2, 1, 4. That seems a little weird, but 1, 2, 3, 4 would be good, right? What's the bottom look like it's doing? 3, 9, 9, 81. Those are all powers of 3. Does that make sense? And so the sort of tricky part of this one is that you have to recognize that this guy is really the same thing as 3 27s. Right? You can cancel off that.
Yes.
And now that pattern is a little more obvious, right? It goes 1, 2, 3, 4. So what should be on the top? The next term? 5. The sign is plus, minus, so it should be plus. And then,
243.
yeah, 243, right? It's 3, 9, 27, 81. So they're powers of 3, so 243. Good. And now we want to try to put this in this form. So let's just start with this. If we put an n up top, right, and so that's going to be our term across the top. It goes 1, 2, 3, 4. So we just call that n. Where do we have to start then?
N equals 1.
N is 1. Okay, good. The bottom is powers of 3.
It's supposed to be negative 3.
Well, I'm going to deal with the negative separately. You could do that as well.
Okay.
But I'm going to pull the negative off on its own. So what powers of 3? I want 3 to the 1 and then 3 squared, 3 cubed, right? So my first term should be 3 to the 1, and so it's okay just to do n. Does that make sense?
Mm-hmm.
You just got to make sure you match it up. If it started with 9, went 9, 27, 81, then you do 3 to the n plus 1, right? You just get to the right power of 3 down the bottom. So now this works perfectly fine, but it ignores the sign, right? The plus or minus. And so I just suggest rather than try to include the negative in here, I would just do negative 1 on its own. And I'll ask you, is that right? Let me ask it a different way. Why is that wrong?
Is that wrong?
That's wrong. So what happens if you plugged in 1 here?
Oh, that's the first one supposed to be 1.
Yeah, so if you plugged in the n equals 1, you get a negative to start with, right? But we want to start positive, so how do we adjust that?
Just
So you put an n plus 1. Does that make sense?
yes.
So that negative 1 to the n or negative 1 to the n plus 1 is just going to be this nice term that makes your sign flip back and forth. And you just make sure you're starting at the right place. Does that make sense? And that's why you don't necessarily want to make it negative 3, because then if you try to adjust that power with the 3, you're going to add new powers of 3, which you don't want. Does that make sense? Now you could have done, right, alternatively you could have done negative 3 to the n and just put a negative out in front of the whole thing. That would have worked as well. Okay. Any other questions or any questions on those? Okay. While we're at it, let's just do this too. Give the first, let's say, 5 terms of okay, so here's a sequence. I'm defining it like this, right? I'm saying a sub 0 is something, a sub n plus 1 is, right, in terms of the other. What kind of sequence, what do we say this is? If we see a sequence defined this way, does that look familiar? Starts with an R. No. Recursive? Does that sound familiar? Doesn't matter. You may not have encountered it yet. That's fine. So this is called a recursive definition, right? So the definition of the sequence refers back to earlier terms in the sequence. And so all we do to define, or to write these out, and I'll just write them up slowly. So a sub 0 is 2. What's a sub 1? Well, the formula says it should be 2 times a sub 0
minus
minus 2, and so in this case, what is it? This one's going to be silly.
2.
It's 2. What's a sub 2? It's 2 times a sub 1 minus 2, which turns out to be 2, right?
2.
So this is a very complicated way to define the sequence that, well, you can just see, right? Each time we're just going to plug 2 back in, and so we're just going to keep getting 2. Does that make sense? But those could be as messy as you want, right? You can get all kinds of crazy things happening, and we'll return to more of this later on. But for right now, just have this basic thing. Let's do one more thing with recursive. All right. Define n factorial using a recursive So again, let's just think about this for a second. What's 0 factorial?
0.
No. What's the definition? 0 factorial is actually defined to be 1. So it's not natural. That's a perfectly reasonable thing to guess. That's the definition of it. It just makes life easier. We'll see why later on. But then the rest of them, I hope, make more sense, right? 2 factorial is 2 times 1. 3 factorial is
3 times.
3 times 2 times 1, and in particular, it's 3 times 2 factorial, right? And 4 factorial is 4 times 3 times 2 times 1, but it's 4 times 3 factorial. Does that make sense?
Okay.
And so when you look at it this way, you can see how to define the term, or a recursive sequence in terms of the previous guys, right? So each one gets called that. So define definition of n factorial. So a sub n is going to be this n factorial. That's what we're looking for. So our first term is just 1, right? That's the 0 factorial. And then once we know an a sub n, right? So this should be your n factorial here. How do you define n plus 1 factorial? So think of the 4 as your n plus 1, right? 4 factorial is 4 times the previous factorial, right? And so that's what the a sub n is. It's your previous factorial, and so what goes here?
n plus 1.
N plus 1, right? The whatever you're defining. And when can we start using this recursive definition? For n, we started at 0. We can start using this once n is greater than or equal to 0. Does that make sense? Okay. We'll see. I don't know that we'll make a ton of use of that, but anyways. All right. So let's talk about limits here. So this is really a recap. We've already talked about limits of sequences back in Calc 1. Remember, sequences are just functions whose sort of domain are the integers, right? Some subset of the integers. And so when you talk about the limit of a sequence, you're talking about the limit as you let n go off to infinity. It's the only way you have a limit. And all the rules you learned for functions will work just fine here. L'Hopital's rule, we're going to apply it without really worrying about it. It doesn't exactly apply here because sequences aren't continuous functions. There's no derivatives in a sequence, but we can still use it because if we know a function approaches some value, if you take the sequence that's defined at the integers, right, it'll approach the same value that that function that was defined everywhere approaches. And so we're going to make use of that without any real discussion, I guess. So let's just say this: evaluate following limits. And again, they're all going to be limits as n goes off to infinity. And so I'm just going to write some of these up. 3. All right, we'll start with some hopefully not too difficult ones. So n is getting huge, right? Going off to infinity. What's 3 over n cubed going to get closer and closer to? 0. Does everybody agree? Right, you got 3, and you're dividing by bigger and bigger numbers. So this is going to go to 0. There's no real work you need to show. Just we'll state this. All right, let's try another one. Okay. Now you see this one, you might know the answer. The answer's, anybody know it? 1/7. I want you to show work to show where that comes from. Okay. So work could be L'Hopital's rule. If you remember L'Hopital's rule, you could do that. But a better approach that's sort of giving you a better idea of what's happening, and I'm going to write this as a separate line. So limit as n goes to infinity. So here's our problem. Okay. And so I'm just going to kind of write this off to the side. As n goes off to infinity, that numerator goes to infinity, right? And the denominator also goes to infinity. And if you remember back, right, if we replace these n's with x's, and I asked the same question, you'd say, oh, that's an indeterminate form, I could use L'Hopital's rule. That's fine, it'll work fine here, but you'd have to apply L'Hopital's rule 3 times. It's pretty silly to do that here, and it doesn't give you a great idea of what's happening. So the idea with any limit is if you can ever get control of what's happening to the denominator, then you can figure out the whole problem, right? If the denominator was just going to 7 and the numerator was going to 8, the whole thing would go to 8/7, right? Or if the denominator is going to 7 and the numerator is going to infinity, infinity over 7 is still infinity, right? So as long as you can get control over the denominator, you're in good shape to determine the limit. And so we get control over the denominator by multiplying by 1 over the biggest power that shows up. Okay? Whatever power that is, if it's first, second, third term, it doesn't matter. It's whatever the biggest power is. It might be a fractional power. And you can't randomly just do that, so you balance it off on the top as well. Okay? So you really just multiplied by 1 here, right? 1 over n cubed over 1 over n cubed is just 1. So now, what's that numerator become? When you multiply 1 over n cubed in, becomes 1 plus, well, it'll get to, the limit will be 0, but let's write it out as 2 over n, right, minus 5 over n cubed. Does that make sense? And then the denominator becomes 7 plus 8 over n cubed. Okay. And so if you were being super formal, maybe you'd even have to do more than this, but I think this is enough for us. Okay, so now what's 2 over n go to? 0. 5 over n cubed? 8 over n cubed? 0. Everything goes to 0 except for the 1 and the 7. Does that make sense? And so I know that can be a little bit tedious, but for now, at least, I want you to show that step. Okay, show that. Once we get into sequence or series, you're going to do this hundreds of times, and at some point I'll stop making you show this step and you can just assume it, but for the first few sections, let's take our time and do this slowly. Let's do one with L'Hopital's rule here. So actually, maybe I'll just write out the problem even before we do it. What's the limit as n goes off to infinity of n times the sine of 1 over n? So we're going to need L'Hopital's rule, but let's look at the form here first before we do anything else. Why can't we just plug this in, the n in? I guess we can't really plug infinity in, but what happens as n goes off to infinity, n goes to infinity. What does 1 over n go to? 0. What's sine of 0? 0. So this is going to infinity times 0. Does that make sense? And so this is an instance or a place where L'Hopital's rule will be useful. This is another indeterminate form, right? If you got something that gets huge times something that gets small, there's a balancing act and you don't know which one's winning out, right? It might go to infinity, it might go to 0, or they might sort of level each other out and go someplace else. So if you remember back in Calc 1, it's been a while, but we turned these indeterminate forms into the infinity over infinity or 0 over 0 forms, and so the natural way to do this one would be to turn it into this. Okay? Right? Rather than multiplying by n, we divide by 1 over n. And now that has a form of 0 over 0, so L'Hopital's rule will apply. So let me just go off to the side and remind you of L'Hopital's rule. There's like 8 different spellings you'll see of L'Hopital's. I think your book doesn't use the S here, right? They use like the little hat or whatever. Doesn't matter. Whatever spelling you like, this is the one I learned originally, and so I stick with it. But L'Hopital's rule says what? The limit, and this is just a abbreviated version of it. Here, I'll do it this way. Okay, so if the limits of f and g both go to infinity or both go to 0, right? And when I say infinity, I mean plus or minus. If you have 2 infinite limits or 2 limits of 0, then the limit of their fraction f over g can be evaluated by doing what? Derivatives, right, of top and the bottom. Does that look familiar? Well, it's been a while since you probably used it. I use a little bit in Calc 2, but we'll make a lot more use of it here. So does that seem familiar? Okay, so let's make use of that here. So in this case, what's our, and again, I'm being lazy here. Technically, that is only for functions, right? Not for sequences. This is a sequence. But this is what if sine of 1 over x over 1 over x goes to some value as x goes to infinity, then the sequence is going to go to that same value. And so we're going to abuse L'Hopital's rule here and use it anyways. So our f is that sine of 1 over n. Our g is the 1 over n. So what's the derivative of sine of 1 over n? Derivative is positive cosine. Integral is negative. So positive cosine of 1 over n. And then are we done or no?
And you get to 1 over n.
Right. So let me just put it like this. Right. Derivative of sine is cosine, so you get cosine of 1 over n, and then you have to kick out the derivative of 1 over n by the chain rule, right? So the derivative of 1 over n is negative 1 over n squared. Remember, let me just give you a little hint if you're not seeing that. That's n to the negative 1, right? So it's negative 1, n to the negative 2. And then the denominator is exact same thing, right? Negative 1 over n to, or negative 1 n to the negative 2, sorry. And so now you do some algebra and clean these up. In this case, those both cancel out, right? And now you just get that. So what's the limit as n goes to infinity? I'll just write it out on a separate line here. Of cosine of 1 over n. Well, 1 over n goes to 0, right? And then cosine of 0 is 1. Is that okay? All right, I'm just going to jot these down on the side. I always debate whether this is worth writing down. But all the limit laws that you're used to from back-forth functions still apply here. And so I'll just write it this way. The limit as n goes to infinity of a constant is just the constant, right? If you have a sequence that's just a constant, you go to there. If you have a constant times a sequence. So you get a new sequence that's c times an, and you take that limit, you just get c constant times the limit. The a sub n's. Right? All of this assumes your limit exists, right? We haven't said anything about what happens when the limit doesn't exist. And so obviously these rules don't apply in that case. Let's try. Okay, so what if I take two sequences? I have a sequence an and a sequence bn. If I know their limits, what's the limit of their sum or their difference? It's the limit of a sub n. So essentially the limit can slide into both pieces, right? If you know what an gets close to and you know what bn gets close to, then an plus bn should get close to the sum of whatever those were. So it's plus the limit of the bn, and then again, if it was minus, it's a minus. So, that make sense? And then maybe I won't write them all out. Write up the first couple. Same thing with a product, right? If an gets close to some value and so does bn, then their product is going to get close to that product. So it'll go to the limit of an times bn. We've already been using these for all the limits we calculated. And maybe I'll stop there and just say review the ones in your book, right? Quotients, same thing holds. Powers, same things hold. Roots, same thing hold. Same things hold. So everything will work there. Okay. So monotone sequences. So this is something that you probably didn't cover a whole lot in Calc 1. So this might be maybe the first new thing. Let's see. Let's define increasing first. So a sequence a sub n is increasing. I didn't write down the formal thing here. Well, let's I'm going to use the same notation as the book, but let's reason this out first. So what does it mean for a sequence to be increasing? So if you got a sequence, you got some A1, some A2, some A3. If you think of this in terms of a graph, right? Sequences are just, you can graph a sequence that's just a point at each of these guys, right? So would that be an increasing sequence? No, because we went up and then we went back down, right? So you're increasing if you just keep getting larger, right? And so how would we state that in terms of the a sub n's? Well, we want each term to be bigger than the term before it, right? And so it's increasing if a sub n plus 1 is greater than a sub n, okay? And this varies from book to book. Some places will make this your definition of increasing. Some books will say if it's greater than or equal to, and then they'll say it's strictly increasing if there's no equal to there. And so let me just double check that and look ahead into it. I want to stick with their definition. Let's see. So they say non-decreasing. Yeah, so they're using increasing and decreasing with just the strict. So this is fine. We'll stick with this. Okay? And then, again, rather than write out the whole definition, that's a waste of time. You can look it up in the book. What changes when we say decreasing now instead? Just that inequality flips over. Does that make sense? And really the important thing, or the big thing, is to really understand what that looks like visually, right? To be increasing or decreasing, and then to be able to apply it to some simple examples. Okay. One more definition. So, I guess we'll do this. And so then it's bounded above. Okay, so again, without being real formal here, here's the sequence. This sequence would not be bounded above, right? It just keeps getting bigger and bigger. But if, say, there's some value and it sort of levels off at that, even if it sort of jumps around all over the place, that's still bounded above, right? There's a cap to how high you ever get. And so a sequence is bounded above if there exists a number, let's just call it capital M, such that, so if you haven't, I don't know if I used this yet, I'll just start. If I write up something, that doesn't look familiar, just let me know. But I use s.t to say such that, so we'll use that often enough that I'll keep abbreviating that. So it's bounded above if there's some number that's bigger than everything, right? So if there's some m such that a sub n is less than or equal to m for all n. And really over here, I really should have said for all n. Does that make sense? And so if we said bounded below, what changes? This isn't bounded below. If I can go like this, right? But if I have some place I level off to, then it's bounded below. And so bounded below if there exists, I'm going to be lazy here, some little m such that now that little m is less than or equal to every a sub n. For all n. Make sense? All right. And it's bounded if it's bounded above it and bounded below. And a sub n is bounded if it's bounded above and below. Okay. And so we have a really important theorem about this. And so this stuff is we're gonna make a lot of use of it when we get to series and determining whether series converge or diverge. We'll try to show you at least one example here before we get to this. So let me just write my theorem like this. If you have a sequence a sub n is bounded and, oh, I was lazy, I forgot to define this. I'm going to define it right in line here. Monotone. So monotone means increasing or decreasing. Okay? So if you say monotone, it means it's either increasing or it's decreasing. One of those two. Okay, and if you have a sequence that's bounded and monotone, then it converges. So we haven't really mentioned any examples that don't converge. But if you think, here, let's do a real easy one. So if you let a sub n equal -1 to the n, so what is that sequence? One, -1, -1, -1, -1, and so on. If you looked at the graph of that guy, right, when n is 0, you're up at 1. When n is 1, you're down at -1. You just get a sequence that looks like that, right? And so does that converge to anything? No, right? You're always going to get terms close to 1 and always get terms close to -1. There's no value that they converge into, right? So this is an example of a non-convergent sequence. Okay, and what we're saying over here is if you have a sequence that's bounded and monotone, then it has to converge. And so I think I'll be very lazy with the proof of this. I'm going to do this. I'm going to say this is a proof, and I'm going to say no, it's not. Cross that out. It's not a proof, but it's some evidence of why this should be true. So suppose you have a sequence that's bounded. That just means there's some lower cap that it never gets below, right? And there's some upper cap that it never gets above. Okay? And so if you're, it takes a little bit of work to give a nice formal proof of this, but the idea is pretty straightforward. If you just, so let's assume A sub n is increasing, okay? So it's monotone, so it's either increasing or decreasing. Let's assume it's increasing. So let's say you start here. Your next term is up above that, right? Your next term is up above it. Next term is up above that. Well, you can only go so high, right? And so you can just see there's got to be some leveling off because you can't go any further than that. Does that make sense? And so writing it out formally is kind of a pain, but sort of the visualizing of it's not too bad. Does that make sense? And so we're going to need that result, but let's not worry about the details of the proof. But just if you have a sequence that's increasing or decreasing and it's bounded, then it's going to converge. Okay? And so let's just try one example just to see how this works. And so we'll come back to a recursive sequence. Consider this sequence. Okay, what I'm about to do here, I don't expect you to come up with on the fly. Okay, this is something you might get into a little bit later on, but for right now, let's just try to follow what I'm saying about it. Okay. So I want to show that this sequence is monotone and bounded. Okay. So we will show. Well, before we even do that. List out the first couple terms of that just to get practice with a recursive sequence again. And then after you do that, you can think about maybe what might this sequence be bounded by. And we can decide if we think it's increasing or decreasing as well. Okay, so a sub 1 was 2. What was a sub 2 then?
4.
4. Is that what everybody's getting? Let me just write it up. 1/2 a sub 1 plus 6, right? Which is 1/2 2 plus 6. And so that's 4. Is that okay? And then you're just going to do the same thing, right? Whatever the previous term will go in to there, right? It'll be 1/2 previous term plus 6. So it'll be 1/2 4 plus 6, so that's 5. 1/2 5 plus 6. Is that okay? 11 over 2, 5.5. That way. 1/2 5.5 plus 6 will be 5.75, right? You could put it as a fraction as well. But what? Anybody have a guess for maybe what this sequence is bounded by? So it's always going to stay positive, right? Because we're going to plug in a positive number and average it with 6. So it'll stay positive.
Same as that one.
Well, so I mean, it won't alternate. You're saying that the -1 to the end vector, you mean?
No, the proof.
Oh, the one that's drawn there?
Yeah.
Well, yeah. So, but what is that actual number that it's capped by on the top? Any guess?
6.
6? I mean, it looks like it's getting closer to 6, right? 4, 5, 5.5, 5.75. It's leveling off. You're always going to be averaging something with 6, and it looks like that thing's always going to be a little smaller than 6. And when you average it with 6, you'll just be pushing closer and closer to 6, right? So that's going to be what we're going to show. We're going to show this thing's bounded above by 6. It's positive, so it's bounded below. And then we'll show that it's increasing. And we'll just do this kind of all at the same time. So this is really sort of an inductive proof. And so if you get a little bit lost on the details here, don't get freaked out. I really just want to get this feel for, okay, this thing's increasing and it's bounded, and so we can do some stuff with it. Okay? So suppose that a sub n is greater than a sub n minus 1. That means it was increasing, right? Between these two terms, we want to show that it keeps increasing. And suppose that a sub n was less than 6. Okay? I want to show that a sub n plus 1 now has both of these properties, the increasing property and the less than 6. Okay? So, let me just do this. A sub n plus 1, what is it by definition? 1/2 of a sub n plus 6. I want to show that it's bigger than a sub n, right? Because I want to show it's increasing. And so all I have to do is look at this formula. I know a sub n is bigger than a sub n plus 1, right? So if I take 1/2 of this plus this, that's bigger than 1/2 of a smaller number, right? Does that make sense? But what is that by definition? That's the definition of a sub n. So a sub n plus 1 is bigger than a sub n. So a sub n is increasing. Okay, so this really, to do it formally, you should do a formal induction on this. I don't want to bog ourselves down too much. This is essentially an induction proof, but I just want to get the feel for what's happening now. Okay? And then a sub n plus 1 is 1/2 a sub n plus 6. That's less than 1/2 of 6 plus 6, right? Because a sub n is less than 6. And so that's equal to 6, right? So your a sub n plus 1 is less than 6 as well. So therefore, every a sub n is less than 6. Does that make sense? Mm-hmm. And they're also positive. And notice the a sub n is greater than 0. And so this sequence is bounded. So like I had said before, a lot of this sort of bounded and increasing stuff is what we're going to use to show that sequences or series converge. We're going to make a little less use of this here. If you become a math major or a minor and you decide to take advanced calculus, then we'll sort of get more into the proofs of these kind of things. But for right now, we just want to touch on it a little bit. But this is valuable now, right? So now we have this sequence that we defined right here was bounded. So let me just write it this way. It's increasing and bounded. Therefore, it must converge. Okay. So let's say, we'll say a sub n converges to L. Okay? So now it satisfies this. A sub n plus 1 is equal to 1/2 a sub n plus 6. So what did we say? A sub n converges to L. So what's this right-hand side converge to? 1/2. That goes to L, does that make sense? Plus
6.
6. What's this side converge to? So if you think about it in terms of its graph, right? If we're saying there's some L that the sequence approaches, what's the difference between a sub n and a sub n plus 1? You're just one term ahead, right? So if a sub n gets close to L, a sub n plus 1 gets close to that same L, right? It's just one term faster. So what does it approach?
L.
Yeah, it's going to approach L as well. Does that make sense? So if these guys are getting closer and closer to L, then this guy will get closer and closer to L as well, right? It's just up ahead of it. So you're going to get to L. And so now we can figure out exactly what that limit was by just doing some algebra here, right? So you multiply 2 across. Let's do it. 2L is L plus 6. I mean, we see our limit of 6 that we thought we'd get. So there's our L equals 6. Make sense? So there's sort of a semi-formal proof that that thing actually goes to 6. Like I said, in reality, you should probably put in some more details. I just want to get a very rough feel for what is happening there. Okay, let's see. Okay, so let's just do one more thing for today, and this should, or for this section, and this should be really quick. I'm going to turn off the lights here. And so I'm just going to have us. Can you guys see that? Okay.
Yeah.
I'm going to shut the shades if you need that. But and we're going to go through multiple of these. I'm just going to stand up here and do it. I know it's a little bit hard to see these stuff. So indicate if the property is consistent with the given graph of a sequence. So we want to decide if this thing's monotone, if it's bounded, if it's convergent. And so I'm not even going to bother writing them down, but let's go through this. So is this thing, well, the easy one, is this bounded? So bounded just means there's some maximum value and some minimum value that it stays between. Yeah, right? It stays between those. You don't have to find out exact values. All you got to realize is it's stuck in that range. So this one's bounded. Is it convergent? So looks like it goes. Am I getting close to a specific value? Yeah, right? It's narrowing in on something. It looks like it is at least. No guarantee whenever you see a graph, but I'd say this thing looks like it's convergent. Looks like you're narrowing in on whatever that, probably 2, right? Looks pretty close to going on 2. So it's convergent. Is it monotone? Up, down, up, down, up, down. So not monotone, right? It's increase, then decrease, increase, decrease. It doesn't stay one or the other. Does that make sense? And so try these on when you get a chance. Look back at them. I didn't want to have to draw a bunch of these, so this is the easiest way to do it. All right, same thing on these guys. Some of them aren't as obvious. So is that thing increasing or decreasing or neither? That looks like it's increasing, right? Is it bounded? It's a little bit hard to tell, but I'm thinking from the trajectory that it's showing here that just keeps going on, right? Looks like it's probably moving along roughly a parabola or something, or a square root kind of function. Not clear, right? There could be a cap up here that it levels off and we just can't tell, but I'd say this is unbounded. It looks like it's continuing to grow for me. And so will it have a limit? If it's unbounded, no. And you might say the limit's infinity, but we still consider that to be not convergent. Okay? So that one would be divergent. What about the next one? Picture. Is that one bounded?
Yes.
Yeah, right. There's some big window you could put around that. They all are inside there, so it's bounded for sure. Is it increasing or decreasing?
No.
It's hard to see that it's here, then here, right? Then here, 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 here. So it's bouncing all over the place. So it's not increasing or decreasing because it goes up and down. And so does it converge? No, because some values get close to whatever that is and some get close to this, right? So that's divergent. Good. And how about this guy? Is it bounded? Yeah, right, because again, remember, it doesn't go off infinitely in this direction, right, to the left, it only goes off this way, and so there's your maximum, whatever that value is the biggest you ever take, and then you're definitely bounded. It looks like this one's leveling off for sure. Is it increasing or decreasing?
Decreasing.
Decreasing, good, and then is there a limit? Looks like there's some limit in there, right?
Yeah.
It'd be hard to guess. Less than 3, more greater than 2, right? Somewhere in there. But there's not enough information to give an exact limit. Does that make sense? Okay. Well, that's good for 12.1. So let's stop there.